We present our paper, Uncertainty-Guided Policy for Active Robotic 3D Reconstruction Using Neural Radiance Fields. In this paper, we leverage neural radiance fields, also called NERF, to tackle the problem of active robotic 3D reconstruction of an object, also known as the next best view problem for object 3D reconstruction. Leveraging the uncertainty modeling in implicit neural representation, we develop a robotic system that actively estimates the next best view for dense 3D reconstruction of an object. To the best of our knowledge, this paper is the first attempt to build an active robotic 3D reconstruction system based on neural representations. NERF approximates the classical volume rendering with discrete samples along array. Consequently, the expected color can be considered as a weighted sum of those samples. The weight distribution will have its peak at the point where the surface is because that is where the light particle will bounce off and contribute to the rendered pixel value of this ray. As the model learns about the underlying geometry, it becomes more certain where the surface is and the samples around it become concentrated and converge to a certain point. Therefore, we can infer the uncertainty of the underlying reconstruction of the object by analyzing the weight distribution. We can evaluate the uncertainty by looking at how spread out the weight distribution is. Here we quantify it by computing the entropy. It fits our purpose flawlessly because evaluating whether a distribution has one sharp peak is in consonance with evaluating the uncertainty of a random variable the distribution yields. Here we show the correlation between 3D mesh and entropy map. The brighter parts indicate higher entropy and therefore more uncertain parts. Those parts correlate reasonably well with noisy parts in 3D meshes. In this work, we investigate a coarse-to-fine reconstruction approach, where we start with a coarse set of images and select views to improve the initial reconstruction. Consequently, we introduce a region clustering, consisting of a region where the initial views are selected and several additional regions where further views can be selected. After an initial reconstruction with the initial view, in each iteration, the view with the highest mean entropy of each sector is selected, and the robot collects the corresponding view. For all the synthetic objects we have tested on, our uncertainty-guided policy obtains the highest F-score against all the baselines, verifying the effectiveness of our approach. We also evaluate our method on real-world objects. Here we present a demo where we run the proposed policy on our robotic platform to reconstruct a toy loader. We first initialize the model with 15 images from the middle circle. Then we collect 12 more images using the uncertainty-guided policy to do the refinement. Arguably, the 3D geometry recovered from the final model using our method has the highest quality even with the smallest number of images, motivating the usage of neural rendering-based models. The proposed uncertainty estimation is easily applicable and can be generalized to the latest advances on neural rendering. We believe our approach opens up a new research direction of using an implicit 3D object representation for the next best view selection problem in robot vision applications. Thank you.